guys are enjoying a beautiful, gorgeous, sunny day, and more importantly, not having to wear masks anymore officially. I, for one, am very happy to see many of your faces. Those of you who want to continue wearing masks, feel free. If you would like me to wear a mask after the lecture is over, if you're talking, please feel free to tell me to do so. Okay? I'm just very happy to see as many of your faces as well, so I don't get my Nathaniels and Carloses confused, because it's just harder to remember names and faces when you only see this much. All right, with that said, we're going to continue today. This is the last class before the midterm. The next class is after spring break. You have a midterm on the 22nd. Everything that we cover until today is part of the midterm syllabus, as posted on the schedule page. I'm going to come over to that side. What I discovered that that's much better. Oh, well, I forgot to turn on it. Yeah, for the midterm, it's closed book, but you can have one cheat sheet, okay? It doesn't really matter one side, two sides. Don't waste your time fine-tuning your micro-engraving technology techniques. It's just not going to be useful. It's not a memory-based exam, okay? If for those of you who think in terms of formulas like this, which formula to apply for this problem, you're not going to do well if you think in terms of formulas. The reason is because you have to still know whether that formula or which formula applies to which problem. So you have to know why the formula is what it is. So it's best not to think in terms of remembering formulas. They're not memory-based things in this course. Not much, very little of it at all. And at least the exam questions won't be testing you on memory, right? But you're still allowed a cheat sheet. Just it's more for your psychological benefit. Okay. Project 1 is due tomorrow. Let's do a clicker poll. The reason I like this is because I can sit. Question is project 1 status. Option A is I have submitted on Gradescope. Option B is I haven't finalized my submission, but I expect to get there by tomorrow. Option C is I haven't, and I don't know if I can do it by tomorrow. I'm in trouble. Okay. A is done. B is doing. We'll get there. C is oh shit, I'm in trouble. In case you didn't notice that project 1 is due tomorrow. 1A is due tomorrow. Okay. Just give me quick clicks, 15 seconds, no more. This information is not going to be used in any way against you, so don't, there's no reason for you to lie. Okay, 54. This is an improvement from 2 days back when it was, I think, 41, if I remember correctly. 32% are confident they'll get there, so that makes it 86. So the remaining 11 students here, and there might be a few more. I don't know if your status is you haven't yet woken up that there's a project due tomorrow. But I have office hours right after class. You might have some of the staff's office hours as well. Piazza probably works more efficiently. A reminder that if you haven't done if you're not following the 2 main tips, one is following the README for Java code examples. Just go through that. And the second is read the documentation of the methods in using. My most common response is likely to be asking you to do this. And if you say you've done that, I will ask you the right questions to get you to help debug your program. I cannot promise I can help debug your program. Ultimately, it's not feasible for somebody to just look at your code and always tell you what's wrong with it. That is your job, right? That is part of any programming assignment. But we will help you if you've done those two things for starters. Okay, for We'll try to help you no matter what, but it'll be much more effective for everyone if you do that. I am very confident that I can get practically every one of you through 1A if you do that, if you make the effort. Okay, 1A is not very difficult. Like I said, it's tens of lines of code at best. Okay, but it's not simply just taking one command you saw in one Python program and just lifting it into a It's not like that. You have to do a little more than that, right? But I'm confident you can all, every person should be able to do it if they spend enough time. It's getting very close, but it is still possible to do it, and it shouldn't take you more than a few hours to proceed systematically. But if you don't, it can take you days, and it can be very frustrating process. All right? So, hope we can get as many of you through 1A as possible. Okay? It's important to be able to do 1A well. It's easy to get 100 on 1A. Okay? All right. Today's topic, we're continuing with reliable data transport. What we saw previously in the last class was a sequence of simple reliable data transport protocols. A category of protocols we call it stop and wait, right? So why do we call them stop and wait? Because they literally send one packet and stop and wait for some information from the other side before proceeding. Equivalently, they have one outstanding packet. The sender has one outstanding packet at any time. Okay. So that's all good. Stop and wait protocol. We came into RDT 3.0. We saw that RDT 3 or 3.0 deals with not only corruption but also with losses. RDT 2.1 and .2, they dealt only with corruption, not with loss. We had to introduce an additional mechanism to deal with loss that we did not need to deal with corruption alone. You send something and you're guaranteed to get some feedback from the other side, because if you send something, something will get there, and if they respond, something will get here. But if that something can be corrupted, that's an easier world to live with than if you send something, nothing at all goes to the other side. That's a harder world. For that, we need timeouts. Timeouts is a neat mechanism we introduced for that. Okay? So let's look at RDT 3.0 in action real quick. This is the no loss scenario. You guys can see that. Okay. That's the no loss scenario where okay, so that's the no loss scenario. These are packet timing diagrams. We'll see a few of these. There might be, probably not a homework question, but there might be a midterm question asking you to show a scenario where something happens. Like, show a scenario where RDT 3.0 that deals with corruption and loss fails to correctly deal with reordering. Okay? RDT 3.0 doesn't deal with reordering, it's corruption and loss. Reordering is a worse problem. So these are examples of timing diagrams. Time, like we've seen before in the HTTP pictures, goes down. The actions are self-explanatory. So this is the no loss good scenario, right? Packet 0, act 0, packet 1, act 1, packet 0, act 0. We're using 1-bit integers, so 0, 1 wraparound, 0, 1 wraparound, right? This is a scenario for packet loss. A packet loss will result in eventually a timeout occurring at the sender, and the sender at that point is going to retransmit, in this case, packet 1 that was lost, and the receiver is going to acknowledge this, life is going to proceed well as usual, right? These are not the only two scenarios that can happen. Some other scenarios that can happen are, instead of a packet, an act can be lost. From the sender's side, in general, There isn't a big difference between this packet 1 getting lost and the packet 1's act 1 getting lost. On the sender side, they are equivalent, right? It's not going to get act 1 at the end of the day. On the receiver side, there's a difference. The receiver side, in one case, got the packet. In the other case, didn't get the packet. That's a big difference. So here's an act loss scenario. In the specific case of RDT 3.0, a packet loss is not any, well, on the sender side in general, there's not much difference. And in this case also, a packet 1's loss that we handle through a timeout. It's the same mechanism we're going to use for act 1's loss on the sender side. Again, it's going to time out and resend packet 1, at which point things will proceed as normal. There's one more anomalous scenario that can happen in addition to packet losses and act losses. The moment you introduce a timeout, there's an aspect of how aggressive your timeout is. In these protocols, as well as in TCP, the value of the timeout, how impatient you are at the sender side, or how patient you are. Right? Impatient means small timeout. Patient means big timeout, large timeout. How patient or impatient you are, or equivalently, the value of the timeout is not important for correctness. It is just an optimization parameter. You can choose to be more patient or more impatient. You can choose a very small timeout value. Sometimes we've seen delays can fluctuate. When we do ping from here to anywhere on the internet, it's not the same value. So if you say, if your pings are normally around 80 milliseconds, and 85 milliseconds have passed since you sent a packet, you didn't get back an act, you decide, okay, timeout, packet's lost. Well, maybe this particular packet was taking 87 milliseconds, it's just getting there, you were too impatient, right? So what timeout you choose? Well, if you're too conservative, you might retransmit unnecessarily, that's overhead. If you're too patient, if you normally 80 milliseconds is what it takes, 80 to 90 is sort of the 95th percentile variance, or 70 to 90, let's say, and your timeout is 250 milliseconds. Okay, that's too much. You're being too patient. What that means is that for 250 milliseconds, the protocol will not make progress. It's a stop and wait protocol. It has to get done with the packet before moving on to the next. So the value of a timeout, what you choose, it's an optimization. It depends. It affects your overhead, but generally not important for correctness. All right, so what happens in this premature timeout delayed act scenario? In this case, what's happening is packet 1 got successfully to the other side, but act 1 was delayed unexpectedly. It could be that packet 1 was delayed and act 1 was sent promptly and came promptly. It wasn't delayed en route. It doesn't matter. From the sender side, there is a premature timeout. Nothing actually went wrong in the network, but there was an unexpected variance in the delay. Okay? Either side. It could be onward or backward or reverse. In this case, there'll again be a timeout. The sender is going to send packet 1 or retransmit packet 1, at which point what's the receiver going to do? It's going to receive packet 1 as a duplicate copy. It has already received a copy of packet 1 before. What do we do when we receive a duplicate copy? In RDT 3.2, you can look at the finite state machine. We said, if we receive a duplicate act, we're simply going to send act 1 again. Okay, we're just going to acknowledge it again. Why are we acknowledging it again? Well, because the sender doesn't know act 1. Or from the receiver's point of view, this act could have gotten lost. So the receiver might think, okay, the sender is retransmitting packet 1 because maybe this act got lost, so I should send this act again. Okay, that's the rationale for the design the way it is. Nothing goes wrong here because you're sending act 1 twice. From the sender's perspective, it's going to receive the first act. Let's say it could receive either act, right? In this case, without reordering, it will receive the first act first and then the second act. When it receives the first act, from its point of view, it doesn't actually know for sure whether this act 1 is this packet 1's act or this packet 1's act. From its point of view, it thinks maybe my packet or that act got lost, and then when this this ACK came, it doesn't really know which of the two, the original or the retransmission it corresponds to. And it doesn't matter. It doesn't matter because it's going to go ahead and send the next inline packet, packet 0 anyway the moment it gets ACK1. And then at this point it's going to get this ACK1 again. The second copy of that ACK1, because nothing bad happened with packet 1 or ACK1. What will the sender do at this point when it receives the second ACK1? Yeah?
Disregard it.
Yeah, that's our finite, that's our state machine. There's not the same, as far as the sender is, if it receives an ACK for the wrong packet, there is nothing to do. In RDT 3.0, in RDT 2, we use the ACK for the wrong packet as an ACK signal. But in RDT 3, we're relying on timeouts. If there's something bad happening about a packet or its ACK, eventually we'll time out and retransmit. So duplicate ACKs can simply be ignored in RDT 3.0. Okay, so timeout is quite powerful. We needed timeouts to deal with loss, but they can also render redundant or obviate some of the retransmission that we were doing in RDT2 that was dealing with just corruption. So having a timeout helps a little bit of the corruption aspects as well, but it's strictly necessary only for loss. Okay? Questions before we, yeah, Jesus.
What if an ACK takes so long to deliver that that ACK was received on like the next iteration?
Yeah, so you have to, oops. That can only happen with reordering. Okay, this protocol doesn't tolerate reordering. This tolerates corruption because checksums as before, right? Let's go back and look at the, oops. I keep moving forward and reversing. Okay, that's our RDT 2.0 protocol. It deals with corruption, so it has methods like is corrupt or not. Like you can see some of that, like C packet not corrupt. And you can do that using checksums. It deals with loss clearly, and that's what we need timeouts for, timers for. But it does not deal with reordering. So you can construct strange scenarios, actually not so strange, these can happen in the real world, where you can show that this protocol breaks under reordering. Okay, you had a question in front from?
I was just thinking, like, would it be possible for the time of the timeout to affect correctness if it's like, if the timeout is shorter, then it's even possible for like even at the fastest performance for the acknowledgement to come back. So like the center just keeps waiting for like less than a millisecond and it sends keeps sending at the same time.
It's a good question. What's your name? Jay. Yeah. I think you've spoken before. So Jay's question is a good one. Any audience class reactions? Is it possible that too low a timeout value, like literally a nanosecond or something, where it's impossible for the packet to have gotten to the other side, the sender just keeps on retransmitting? Is it possible to break correctness? So let's go to the premature timeout picture. This is the premature timeout picture. And mentally try to imagine, I'll play the rest as well. Mentally try to imagine that timeout value being like an infinitesimal value. Could something go wrong? What will happen in Jay's scenario is this packet 1 will be sent and then there will be a timeout again, a packet 1, packet 1, packet 1. Let's say 20,000 packet 1s are being sent just stupidly, right? Because the timeout is so bad, so low. What's going to happen? Yeah?
The ACK one is slightly longer, it's gonna come, it's gonna stop it at some point, assuming it's nanosecond, it's gonna be at some one, despite the fact that a nanosecond is so small, at least one of them is gonna hit.
Yeah. From the sender's perspective, that leaves my chalk, there was only one. It's right there. The sender's perspective, we were doing packet 1, Okay? If it sends a whole bunch of closely spaced packet ones because it's timing out over and over because it's just a badly configured timeout. These are all packet ones. Okay? Each of those, let's say all of them get there or most of them get there. It really doesn't matter. The acts are going to look like that. Some may be lost, it doesn't matter. These are all act ones. Okay, if you look at this picture, we are ignoring from the sender's side any redundant act ones after the first act one. The sender will not send the next packet, which is packet 0 here, until it gets at least one act one. This is what a stop and wait protocol is. You get done with the current packet before moving to the next packet. In this case, the current is packet 1, the next is packet 0. So it will never send packet 0 until it gets, from its perspective, act 1 has arrived. Once it's done with packet 1, after the first act 1 has arrived, any more act 1s, 20,000 of them, if they came, will be ignored because it's working on packet 0. It will now wait for packet 0's act. Question?
This, could this be technically the fastest way to send the packet? If you keep sending it, if you keep sending it to the receiver, and then just get.
I know.
I had a similar question, like if you watch it reliability, we're doing that TCP, what's stopping you from sending a second time like twice on 60 miles? Because like you're still gonna get the same app, it's not gonna be that much slower, and you're just like increasingly reliable. Like why can't Zoom just like do this as their TCP connect, like ensure that, you know, you're not like facing delays for any sender really.
So Anand's question is, why don't we just do this as a common case? Like just send each packet twice over or thrice over. Any responses? It's a good question. Yeah?
Lot of overhead.
Overhead, right? So if you're, let's say your success probability is 99.9%. Most of them packets do get to the other side. Okay? We don't deliberately build rotten networks where bad things can happen. It's just we don't know how to build perfect networks. This goes back to 1950s to Claude Shannon, electrical engineer, one of the fathers, or maybe the father of information theory, where it's well understood that there are limits to how reliably bits can be sent on any channel, wired or wireless. Okay? We can make the probability smaller and smaller. We don't know how to make it 0. However, if the probability P is very small, let's say 1 in 10,000 packets get lost. Even 1 in 100, it doesn't matter. Okay? There's a let's make that 1 in 100. Okay, 1% loss rates are pretty bad network these days. We don't have these high loss rates. At about 4 or 5% loss rates, TCP will just stop working. It'll be terrible in performance. Okay, so 1% is a pretty high loss rate. 1% means 1 in 100 packets get lost. There's a 1 in 100 chance that your packet's going to get lost, and you're sending every packet twice over, doubling the overhead, which is not a good trade-off, right? If you were charged $1 for transmitting a packet, you're paying $2 for a packet, and there's only a 1 in 100 chance that the second dollar will be actually useful. So we don't do this as a matter of course. We retransmit when we have a reason to think that something bad happened. Okay, other questions? Okay, so moving on to today's topic, or the bulk of today's topic, which is performance.
Just a question. So, can there be a situation where a previous packet zero's acknowledgement comes after the first acknowledgement of packet one's?
Good question. What's your name?
Anurag.
Anurag. So this is again a question related, similar to GC's question on reordering. Okay. Essentially, if you try to break this protocol by playing with delays, like stretching some arrows too far below and compared to when they were sent, you'll find that unless you reorder, you'll not be able to break this protocol. It's the correct protocol. but it doesn't tolerate reordering. So let's look at an example of why it doesn't tolerate reordering. Okay. Can someone give me an example of why it doesn't tolerate it? This will help answer your question as well. Yeah?
Well, if the sender sends packet 0, and then the acknowledgement for the first packet 0 is really, really long. And then it would time out and send another packet 0. And then you get the acknowledgement for the second packet 0.
This packet,
Yes.
do you want it like this or like?
Oh, no, that's just the. And then send packet 1. And then the acknowledgement for packet 1. Then we set packet 0. And that one doesn't make it. That's
Very good. What's mind your name?
I'm Joe.
Joe. This is very good. Okay. We did something really weird here. Okay. And I think this helps answer your question too, right? This, what's wrong here? This packet 0 is the first packet. This packet 0 is the third packet. Remember we have 1-bit integers that wrap around. Okay, so 0, 1, 0 is like 1, 2, and 3. Okay. This was a retransmission. The sender knows it's a retransmission. But at this place, or sorry, at this place, the sender is sending packet 1 because it got this acknowledgement. And it also got this A1 for the second packet, the acknowledgement in a timely manner. And now it has sent this packet 0. Let's assume this packet 0 got lost. In reality, the third packet got lost. When the sender receives this ACK0 here, it's going to think this packet 0 went through fine, and it's going to move on to packet 1. But we missed a packet in between. That's the problem. That's why it doesn't deal with reordering. Okay, reordering is, it's worse. Okay, there's corruption, there's loss, there's reordering. So there's different kinds of devils that need different mechanisms. Now reordering can be dealt with just these same mechanisms, just we have to be a little more careful. This simple protocol is just not good enough. TCP does deal with reordering, we'll see how it deals with it. Daniel.
Could you include the checksum in the ACK? Wouldn't that sort of solve this problem?
Include the checksum in the ACK. That's one way to do it, with a high probability. Again, checksums can match for different content. It's just a better way to do it. You don't. It's not perfect, so it's technically not correct, but it's a little bit too clever, I would say. It's not needed. If we just use sequence numbers that are longer than, in this case, the reason we were able to show this problem is because the 0 appeared again. But if you had a long sequence space, an 32-bit integer sequence space, the 0 is not going to reappear anytime soon. You have to send 4 billion packets before you reuse the sequence number. So that alone, in practice, is enough to deal with reordering. If every packet is stamped with a sequence number, 23, 24, 2,446, 97 trillion, well not, it doesn't go to trillion, 97,446 or something. The reordering problems won't occur until it wraps around. So that alone takes care of it. We don't need to use checksums for that. And checksums, because of collision, will actually be buggy in that case. So that's an interesting suggestion. I'm gonna put that. Okay, let's move on. The performance of the RDT class or stop and wait protocols we've seen sucks. TCP doesn't work as a stop and wait protocol. We saw a stop and wait protocol in the interest of minimalism, to see the simplest scenarios, simplest protocols that are correct without worrying about performance. This is the right way to design any distributed protocol. You first optimize for safety or correctness. If your protocol is not correct, everything else, how fast it is not a relevant question. Nobody's interested in the question. So you first make it correct and then you worry about how to improve performance, okay? That's why we're doing this. And the simpler the mechanisms are, it's easier to understand what is needed for what, so that you're not making a protocol unnecessarily more complicated than it needs to be, okay? Because mechanisms have overheads, so we don't want to use mechanisms that we don't really need. All right, so how do we look at the performance of stop and wait protocols? If you're sending a packet from here to the West Coast, the utilization of this, the throughput, bits per second capacity, how fast you can send data to the other side. With a stop and wait protocol is going to be pretty slow, okay? So here are some example numbers. Let's assume a 1 Gbps link. Most of us actually don't have a 1 Gbps link, but you could plug in 10 Mbps, which is a common broadband capacity, or 100 Mbps, whatever it is that you have. 1 Gbps is more like what most departments at UMass have to the gateway, and the gateway is at least 10 Gbps or more at UMass. But let's stick with this example, 1 Gbps, 15 milliseconds, right? If you just switch the numbers to 100 Mbps and 150 milliseconds, which would be going further out, nothing, it will be very similar conclusion. The time to transmit a packet, the transmission delay size of the packet divided by the speed of the link in bits per second. We've seen the first kind of delay we've seen in this course, and that turns out in this case to be 8 microseconds. So on the sender side, we're doing 8 microseconds of useful work on this channel. We can keep pumping at 1 gigabit per second. That is what the transmission capacity is. But to send one packet only took us 8 microseconds. And then it is going to take 15 milliseconds of one-way delay, which is 15,000 times, well, not 15,000 times, but some thousands of times more than that 8 microsecond. And then 15 milliseconds for the app to come back. And then you spend 8 microseconds pumping data in. So once every 30 milliseconds, you're pumping 8 microseconds into the network. You're pumping 8,000 bits into the network. So you're doing only useful work for a small fraction of time. So we calculated, like shown in this picture, that says, oops, that shows that blue band on the top, that is equivalent to that 8 microseconds, the transmission delay. And then you're waiting for one round trip after the transmission delay for the acknowledgement to come back. We're assuming that the acknowledgement is just tiny, so it's negligible transmission delay, which is a reasonable assumption in practice. So it is only when the ACK arrives at time t equals the round trip plus transmission delay of the sent packet, the first sent packet, that the second packet will be sent. Packet 0, packet 1. Its utilization is going to be really poor, okay? Its utilization is going, so what's the utilization? The utilization is the fraction of time that we are doing useful work, which means the remaining fraction of the time we are idling. We could have been using the resource. We're just wasting resource the rest of the time. So we're wasting this whole time. We're not transmitting when we could have been shoving packets on our end. Okay, back to back. That's what pipelining means. That's the total amount of time of which, in the denominator, of which we are only doing useful work for the numerator amount of time. Transmission delay divided by transmission delay plus round trip. Okay. So this is the useful fraction of time, and this whole time is the total time that gives us the utilization. So if you do that math, that's 8 microseconds divided by 30 milliseconds plus 8 microseconds. 30 milliseconds plus 15 milliseconds, 15 milliseconds in our example. And that's a very bad number. Okay? The closer to 1 the utilization is, the more efficient the protocol is. So we're basically just idling away like 99.9 plus % of the time. We want to be not so idle, we want to be more efficient than this. It's the structure or the nature, the design of this, the stop and wait design of the RDT 3.0 protocol that's limiting our performance. So that's where pipelining comes into the picture. Instead of sending one packet from one end and wait for a long time, because light takes that much time to go and come back, that's propagation delay. We are instead going to send a window of packets from one end. So instead of sending one, we're going to send a few and then wait for all the acknowledgements to pour in. That is what's called pipeline, because we can do it. Why not? We can send the second packet even as the first packet is going along the wire. So here's the improved utilization picture. In this example, what we have done is we've gone from a window of one packet in stop and wait protocols to a window of, in this example, 3 packets. You send 3 packets at a time, wait for acknowledgements, and then send the next 3 packets. What happens to our utilization? How much does our utilization increase? We go a window from 1 to 3, yeah?
A factor of 3.
Yeah, well, just a factor of 3. If you send 4 packets, you get a factor of 4. Send 5 packets, you get a factor of 5. There is a limit. What is that limit? Well, so factor of 3 utilization, that's the same math as before. Like before, instead of doing just one transmission, we're doing useful work for 3 times L over R and then idling for this RTT time, after which again we're doing useful work. So 3L over R divided by RTT plus 3 over L, 3L over R is a fraction of useful work. If we send 4, in this picture it's clear that our throughput will quadruple, 5 will quintuple, and so on. How long can we keep doing this? Yeah?
RTT divided by L over R.
RTT divided by L over R, is that right? How many people, raise your hands if you think it's RTT divided by L over R. No, just 1 or 2 people. So the rest think it's not RTT divided, so what is it if you don't think it's RTT divided by L over R?
It's RTT plus L over R divided by L over R. So RTT over L over R plus 1.
Does that make sense? The person who said RTT, what's your name? The red shirt. Sorry?
Lenny.
Lenny.
Yeah.
Does that make sense? Let's just look at the picture, right? We send 1 packet and we are waiting for RTT more time. The total length of this time is RTT plus L over R. How many L over R's can we fit in the time RTT plus L over R? That's this, right? At that point, you would have hit this point. If beyond this, you try sending even more without stopping for acknowledgements, what will happen is the queue will start building up just locally. Because your machine is not going to be able to shove packets fast enough on the wire. Okay? Okay. So pipelining is an easy way to increase throughput, provided you design your protocol correctly to handle pipelining. We saw that it was fairly non-trivial to design even a stop and wait, a single bit sequence number based protocol. So we need to be really careful in pipeline protocols, right? All right, well, I have some clicker questions. Why don't we do some clicker questions and then we'll go back and discuss it. Oh, you can't see it, sorry. Sorry, this is the question. Yeah, we'll just read that. I think that's like 90% or something of the students or more, so 5, 4, 3, 2, 1. Okay, I think this should be pretty easy, but looks like it's not. I don't know if it's because I went back and forth reading different questions, but yeah, this is a problem, so I need to spend some time on this. Which of the following are needed for reliable data transfer with only packet corruption, no loss in reordering, only use as much as required? With packet corruption alone, we had to use checksums for sure. Okay. With checksums, we were able to detect if a packet was corrupted or not. If a packet was corrupted, we had to retransmit a packet. We needed retransmissions. The moment you retransmit, we had the disambiguation problem. Cat, dog, dog. Is the second dog a duplicate in the data or a retransmission of the first dog? To deal with that, we had to use sequence numbers. So we needed sequence numbers as well as checksums to deal with the corruption alone. So we need checksums, and we of course used ACKs. We also saw a protocol with ACKs and NACKs, ACKs and negative acknowledgements. But we subsequently saw that negative acknowledgements were redundant. We could do whatever we want with just ACKs. We didn't need both ACKs and NACKs. We do, however, need sequence numbers. The moment you retransmit, you need sequence numbers. Therefore, D would be the right answer. Checksums, ACKs, and sequence numbers. Checksums, ACKs, NACKs is incomplete. Checksums, ACKs, NACKs, sequence numbers is more than incomplete. Okay? So this is a very low percentage, and I'm clearly not communicating to you. Hopefully, let's try this. I'll wait till 7 and count down. Five, four, three, two, one. D, checksums, ACKs, sequence numbers, towns. That is good. Because most of you got it right, I won't dwell on it. Okay. So this question, I just included RDT 2.1 and 2.2 just because you may not remember exactly what it is. But working through the details of the FSM to answer this question is probably going to take a while. I think you should be able to really answer this question without having to work through the details of this protocol. But let's see how you do. Five, four, three, two, one. Okay. There's a lot of colorful university of answers. Okay, this is a little bit non-trivial. So this is not surprising. I think the first question was a little surprising. What are the choices? The choices are saying it's still correct. Reliable in order delivery. So that's wrong because we didn't design for loss. Reliable in order delivery is still achieved. This is wrong. You can't get reliable in order delivery without using timeouts and packet loss and others. So it's one of the other two choices. So that should have been easy to rule out A. If the protocol gets stuck, protocol will continue making progress, we skip delivery to the next. So that's saying 1, 2, packet 1, 2, 3, 4 in the 1-bit integer space, of course. instead of being received as 1, 2, 3, 4, it might be received as 1, 3, 4, or 1, 4, or 1, 2, 4, or 2, 3, or 2, 4. So there might be gaps, but order will be maintained, is what C is saying. Well, if you look at, you don't have to work through the details of the every step in this protocol to answer this particular question. In general, you would have to. If I say break the protocol, the show scenario where the protocol breaks, you have to look at the protocol carefully. But this whole protocol, the RDG 2.1 or 2, that whole 2 dot star protocols were designed assuming that if you send something, something will come back. That is what allowed the sender to make progress. The loss can happen, the sender sends something, it gets nothing back, it will be stuck because the receiver has no reason to do anything. The receiver is completely responsive, reactive, right? So you can check this from their FSM design as well. We're waiting for a packet from above, we send a packet and we will wait for an ACK or NAC or 0. We will just be here for it. Right? Nothing will come back and nothing may come back if a loss happens. Therefore, that's the right answer. We did this one. Okay. This should be very easy. Five, 4, 3, 2, 1, 0. Okay. So we're going to see 2 classes of protocols called go back N and selective repeat, the GTN and selective SR. TCP is primarily based on go back N class of protocols, but it also supports selective repeat as an option. So we're going to be looking at both before looking, and then we'll have enough of the principles, the basic mechanisms, textbook concepts needed to understand and appreciate what exactly, how TCP composes these mechanisms, why it does what it does. Both go back in and selective repeat classes of protocols are pipeline protocols. Pipeline protocols have a window. So that window, that 3x, 4x, 5x, that's the window we're talking about. We send a window of packets out and we wait for a bunch of acknowledgements to stream back in. So for this window of packets, we'll maintain a k-bit sequence number now. We don't need to be so stingy anymore, economical in our sequence number space, because we move past the pedagogical goals here. It's just easier to deal with longer integers for sequence numbers because wraparound problems are likely to be less, right? So let's just assume that you have, k-bit sequence numbers. K is comfortably long, like integers, for example. And n is what we'll use to denote the window size, which means if n is equal to, let's say, 10, you can send up to 10 packets out before you get an acknowledgement for any one of those packets. Why not send as many as you want? Why is there a limit? Why is it 10? Well, this number 10 will change depending on how much congestion is in the network. But for now, we'll assume it's a constant. We saw that there's a limit to how much the window can be, because the moment you get to like that number, we saw that there's no point. We'll just incur queuing delays. We can't send any more of a window than that number. That number depends on the network parameters. In TCP, it can also depend on congestion parameters. For simplicity, we'll just assume that there's a number n. That's the maximum window size that you can jump into the network before you're forced to wait for at least one of them to be acknowledged. Okay? You go back n, the picture of the sender side looks like this. An important thing to notice about this picture is it's a sequence of contiguous colors. It's green, yellow, blue, and then just white, I guess. We'll see that in the next class of protocols, it's not quite like this. there is a prefix of packets up to a certain sequence number, that's 3. That means these are the packets at the sender side that the sender knows it has not only sent, but the receiver has already acknowledged and the sender has received those acknowledgements. So the sender knows that everything up to here has been received by the receiver. This is the picture at the sender side. The send base is the first sequence number. So everything in the packet 22 has been acknowledged successfully by the receiver. This is packet 22. Okay? That's send base. The first packet that's been sent but not acknowledged is send base. And then there's a certain number of packets the sender has sent, after which there is a range of sequence numbers that the sender could use to send, but it hasn't done so. This is because the application hasn't asked TCP or this transport protocol to send anything. It only had this much data, there's nothing more to send. It could send, if the app asked you to send more, it could use these sequence numbers to send. But it cannot use the sequence number because the window size is limited to n, because then we'll be sending too fast. What is that n? Like I said, it's a constant for now. We won't right now worry about where it came from. We'll worry about it later. Okay, so that's your window size. Our acknowledgements, this is the sender view. The acknowledgements are going to be cumulative. Go back inside protocols use cumulative acknowledgements. What does cumulative acknowledgement mean? What it means is, this is the interpretation. ACK of n means everything up to and including sequence number n has successfully been received by the receiver. So the receiver sends ACK 22. It is saying, I have received all packets up to 22. So 22, 21, 20, 19, 80, all those. This has a problem. Okay, this has an advantage. If a sender sends a burst of packets, say it sends a burst of 20 packets. The receiver receives all of them successfully, the first 20 packets. It can simply send ACK 20, one acknowledgement, just say, I received everything. Instead of saying ACK 1, ACK 2, ACK 3, ACK 4, and so on. So it helps compress the ACK overhead, reduce the ACK overhead, cumulative acknowledgements. It of course creates a tricky situation. If the sender received everything up to 15, and then it didn't get 16 and 17, but it got 18, 19, and 20. In this case, the receiver can only send ACK 15. It cannot send ACK 20. It has no way to communicate that it got up to 15 everything, and then after that there's some holes. It doesn't have a way to communicate that. So in the case of successful receipt of all the packets in the window, it can just send the biggest cumulative sequence number as in the acknowledgement. But if there are holes, it cannot communicate in ACK 15 that it also got 18, 19, and 20. That's how cumulative acknowledgements work. This protocol deals with loss, so it must have a timer. There is a timer. There's only one timer in Go Backend protocols. We think of this timer as being for the oldest in-flight packet, which is this. This is the oldest in-flight packet. This packet has been acknowledged by the receiver. When a timeout occurs, what do? A timeout occurs while waiting on this packet. Let's say this is packet 15. And the receiver has received everything up, or let's say this is packet 16, continuing with the previous example. The receiver has received everything by 15. The sender times out on packet 16. It is going to retransmit 16 onwards, whatever it has sent before. Even though at the receiver hasn't received 16 and 17, but it did receive 18, 19, and 20. But because they couldn't communicate this, the receiver couldn't communicate this exact information to the sender will simply, when it times out in packet 16, it will retransmit everything in the current window that had previously sent, so 16 to 20 here. If this was 20, right? Okay, so that's how this works. The receiver is very simple. This is the benefit of Go Backend. Especially during TCP's early days, there were some performance considerations that are not so relevant these days. But back when machines were run slower, every single optimization every single, any mechanism that was redundant would not be there. They would try to keep things as simple as possible, right? Go back and receivers are very simple. If the receiver gets the next expected packet, it has everything up to 15. If it gets 16, great, send back 16. If it's expecting 16 and it gets 17, what does it do with this packet 17? For the acknowledgement, it can only send ACK 15 still. It cannot do it, it cannot say anything more than ACK 15. Because it didn't get 16, it got 17. Out of order packets like this 17th packet in this example, the receiver can either buffer it or discard it. It doesn't matter. The sender is going to retransmit that 17 eventually again anyway. In practice, of course, we do buffer it, but this is not important for correctness. The receiver needs to keep only one number, the receive base. The next number 16 is what I'm waiting for. If I get 16, I send ACK 16. If I get anything else, I don't have to really bother. I don't even have to buffer it. Although practical implementation will buffer it because there might be some reordering. Okay, and says here on receipt of out of order packet can discard, react packet with the highest in order sequence number. So if I'm expecting 16, but I get 17, I'm going to ACK 15. Any question?
I'm confused what you mean by buffering.
Oh, the receiver is expecting this packet, let's say this is packet 16, and it gets packet 17 but not 16. What does it do with this packet 17? The application is expecting packet 17, right? This is a socket where this protocol is executing. The application on top is waiting for data delivery from this socket. It cannot give packet 17 to the application, because that will break order. 16 has to go before 17. So it will keep this buffered in the socket, stored locally, is what buffering means, or discard it. Right? The thing is, it could do either, it doesn't matter for correctness, but practical implementations will of course buffer on the receiver side. PCP spec, for example, doesn't say that you have to do one or the other, right? It leaves that to open as an implementation custom. PCP is closer to go back in the protocol. Okay, so let's look at this protocol in action. It's a fairly simple protocol to understand, but in action there can be some non-trivial corner cases, so we want to understand this fairly carefully. Both go back and select overview. So this is a protocol where the window size is 4. Just a simple, this is a go back an instance where the window size n is 4. So you can send at most up to 4 packets out before at least one of them is acknowledged. At which point you can send one more packet out. But you can't have more than 4 outstanding that are unacknowledged at the center. So here it's sending packets 0, 1, packets 0, 1, 2, and 3. And it's going to wait for acknowledgements because 4 is the window size limit. And let's say packet 2 gets lost. In this case, it will get ACK for 0, 1, and 3. At some point it's going to receive ACK 0, it's going to send at that point packet 4. The window is sliding. The window slid from 0, 1, 2, 3 to 1, 2, 3, 4. As soon as ACK 0, right? We moved this. This is called a sliding window. It slid from 0, 1, 2, 3 to 1, 2, 3, 4. As soon as ACK 2 arrived, it slid to 2, 3, 4, 5. Now this 2, 3, 4, 5 is the current window it's operating on. It will get ACK 3. Which is the packet that got lost? The third packet got lost. So it won't get ACK 2, but it is getting ACK 3 here, okay? Sorry, it's getting the ACK for the packet, the ACK that's spawned by the receipt of packet 3, but it's not ACK 3 because we're dealing with cumulative ACKs. So the receiver can say, I have received everything up to packet 0, I have received everything to packet 1. Here it cannot say, I have received everything up to packet 1 and then I didn't receive 2 and then but I received 3. We don't have this language of cumulative acknowledgements. So it's simply going to resend ACK1, which is the highest sequence number up to which every receiver is cumulatively received everything. Okay, that's how cumulative ACKs are working. From the sender's perspective, it's just a do-back. It's going to ignore that, but at some point, there will be a timeout for packet 2. We think there's always just one timer, and that timer is always thought of as the being or corresponding to the oldest unacknowledged packet. In this example, it's packet 2. When that timeout happens, it's eventually going to retransmit the whole window again, 2, 3, 4, 5. It timed out on 2, but it doesn't know that 3, 4, or 5 were received correctly at the receiver either. This is the problem with cumulative acknowledgements. All it knows is 2 didn't get to the receiver, so I have to start from 2. I might as well retransmit 3, 4, and 6, because I don't know which ones among 3, 4, and 5. That the sender knows it was transmitted at least once. Which ones didn't get to the receiver, the sender doesn't know. So it's going to retransmit the whole window. Okay, that's the downside. The benefit was the receiver is very simple, needs to keep just one variable, and you get ACK overhead reduction because you send one ACK. You could potentially send one ACK for many packets if you're getting everything as expected. In the common case, when loss rates are really low, that's a good optimization. Losses are not happening that frequently. Usually you're getting things fine in the order they are sent. You're not guaranteed that, but usually you're getting that. And so cumulative acknowledgements are a good optimization for that common case. Selective repeat is not using cumulative acknowledgements. Instead of saying at n means I have received everything up to and including n cumulatively, selective repeat is doing the more intuitive thing. If I get packet 0, I send ACK 0. If I next get packet 4, I'll send ACK 4. A packet and ACK match in sequence numbers, one ACK for each packet. That's selective repeat. It's called selective repeat because repeat is retransmissions. If something is missing, only that thing has to be retransmitted, not the whole window that can go back. So individual acknowledgements, receiver will in general buffer packets for eventually in order delivery to the application on top. The sender is going to time out and retransmit individually from an acknowledged packet. It's not the whole window that can go back in. We maintain a timer, of course, because timers are needed to handle loss. Unlike go back n, where the timer was for the oldest unacknowledged packet, the first yellow packet. In selective repeat, there's one timer for each packet. Packets are just separate. There's an ACK for each packet, there's a timer for each packet. Timers are cheap, so it doesn't cost that much to maintain them, right? You just keep a scheduler and thread it fires. So as before, we'll assume that the sender has a window size limit of n that limits like which sequence numbers can be used or not used. So this is the picture to keep in mind. Like I said, it's different from go back n. And the main difference is, unlike go back n, where we had a contiguous stretch of colors followed by another contiguous stretch of colors followed by and so on, here you're seeing some interspersing of colors. These are packets that have been sent by the receiver and acknowledged. These are not green, however. In the textbook, there's no difference for this color, but it's actually best to think of these sequence numbers as not usable. It'll become clear in like a couple of minutes why these are marked as not usable, even though in practice these are packets just like in go back n that have been sent and successfully acknowledged by the receiver, and the sender has received those acknowledgements. Okay. So this part is actually similar to go back n. This is the first unacknowledged packet. The yellow packets are packets that have been sent by the sender, but not yet acknowledged by the receiver, from the sender's point of view. So these are the packets that the sender hasn't received an acknowledgement for. These are packets that the sender has received acknowledgement for. We are no longer dealing with cumulative acknowledgements. So you can have some that are acknowledged, some that are not acknowledged, followed by some that are acknowledged. So that's why you see this interspersing between yellow and green. And then these are packets like before that the sender could use, but the app hasn't written anything yet, so it's not using them. But even if the app wrote something, there was more work to do, it cannot go beyond this because of the window size. from the receiver's point of view, it's a little bit more complicated than go back N. These are packets, this is the prefix of packets up to which it has received everything. Just like on the sender side, the receiver can also have interspersing of colors. The receiver has received everything up to 15. It didn't receive 16. Purple packets are packets that are out of order buffered. So it received 17, it received 18, it didn't receive 19, it received 20. And these are not expected to be received because they haven't been sent yet. So these are the examples of gaps in the in-order delivery. In go back N, we would send an ACK for this packet saying this is the highest up to which we have received everything. In selective repeat, we would say ACK, we won't send ACK 16. This is 15, this is 16. But we will send ACK 17, ACK 18. We won't send ACK 19, we will send ACK 20. We'll send an ACK for whatever we receive. Okay? So that's the sender side. We no longer dealing with finite state machines. It's just not feasible to represent these as finite state machines. Visually, it doesn't help. So pseudocode or code, pseudocode is the better way to do it. The sender gets data from above. It's going to, this is event action. If this event happens, you take this action. If it gets, sorry. Oh, that's fine. If it gets data from above, if that's the next available sequence number in the window, send packet. What is that if next available sequence number in window? Well, if the sender has any of these blue slots left, it can send. If it doesn't have any blue slots left, that N limit has been reached. That's what it's saying. If there's a timeout for sequence number N, simply retransmit sequence number N and restart the timer for sequence number N. There's one timer for each packet. Go back in, there's one timer for everything. Or not, you think of it as a timer for the oldest unacknowledged packet. Here, there's one for each packet. If it gets an acknowledgement for N in the send base and send base plus N, so let's go back and look at what that is. Oops. If it gets an acknowledgement for any packet here, send base and send base plus N, then it is going to mark that packet N as received. So it's going to flip its color from yellow to green. And if N is the smallest unacknowledged packet, you advance window base to the next unpacked packet. If it gets an acknowledgement for this packet, it'll advance send base here. But if it gets an acknowledgement for this packet, it cannot advance send base. Send base will remain here, this will simply come green. Okay? So the sender is just keeping track of what acknowledgement is receiving. At the receiver side, if the packet is in the receive base and to receive base plus N minus 1, so let's go back and see what that means. So that's receive base until this any of the packets that it could receive in that window. It is going to send an acknowledgement for just that packet. There's one ACK for each packet. If it gets any out of order packets, like these purple packets, the purple packets are out of order because there is this gray packet that is expected but not yet received. Then it is just going to buffer those packets. Reordering is expected, we have individual acknowledgements. Why waste something? Again, if it didn't buffer them, there's a difference here between go back and select or repeat. Go back and we say if it didn't buffer them, it's fine, it's not important for practice. In this protocol, it should buffer them because if it received a packet, it already acknowledged that packet to the sender saying, I have received it. It better buffer because the sender is thinking that the receiver has this packet now. So even if it's out of order, with the pseudocode, the receiver should buffer it, otherwise it will get stuck. The protocol may get stuck. If it gets an in-order packet, then you deliver the buffered packet to the application and advance the window. So let's go back to the picture. If it gets this packet, you move the receive base to the next value. This will become green, and this packet is ready to be delivered up to the application that's waiting on the socket to receive method. Read, receive from whatever language, whatever method you use. If the packet N is in receive base minus N to receive base minus 1, then you simply send an acknowledgement for N, otherwise you ignore it. What is this thing? Receive base minus N to receive base minus 1. Let's go back. Receive base is here. Receive receive base minus n to receive base minus 1. So there's some window of packets here that pseudocode is talking about here. Okay. It is saying if you receive a packet here, you still acknowledge it. If you receive sort of in this window of n, if you receive a packet from way back, you can ignore it. Why might the receiver receive one of these packets when it has already acknowledged them before? Yeah.
Or the acknowledgement never reaches.
Yeah. The acknowledgement could have gotten lost or gotten delayed. The sender may have may retransmit this packet or this packet. The receiver has actually gotten it fine. The sender doesn't know the receiver's gotten it fine. So if it gets a packet here, it better send an acknowledgement. Right? So that's it. There is so this is selective repeat in action. Packet 0, 1, 2, 3, 4 came on the window side with 4. Okay. Packet 2 gets lost, just the third packet, packet 2, just like in the previous example, gets lost. There's going to be a forced timeout at some point. Every successful acknowledgement will release one more packet from the sender side, sliding window. So it moves from 0, 1, 2, 3 to 1, 2, 3, 4, to the next 1, 2, 3, 4, 5. That's the current window. At this point, packet 6 cannot be sent until Act 2 has arrived. Okay. But if Act 2 doesn't arrive and instead Act 3 arrives, in selective repeat, we can release one more packet. We still have a few minutes. Hang on. Let's finish this example. When Act 3 arrives, go back and when Act 3 arrives and Act 2 hadn't arrived, the sender couldn't advance this window. But here, when Act 3 arrives, the sender now knows exactly the state of affairs that's likely at the receiver. The packet 0 has been received, 1 has been received, 2 hasn't been received yet as far as the sender knows. 3 has been received. And when packet 2 times out, it is going to retransmit just packet 2, not 3, 4, and 5. 3 has already been acknowledged, so there's no need to retransmit it. 4 and 5, the acknowledgements may or may not have arrived yet, but because we are no longer using go back n, we're using one act per packet per sequence number. Until the sender knows for sure that that packet has timed out, until 4 or 5 times out, it doesn't need to retransmit 4 or 5. Okay? So I'll stop there. The next time we meet, it'll be a class after midterm. We'll give you a chapter in the midterm. Good luck for the midterm. Good luck for project 1A.